In this video, we present our work, A Good Foundation is Worth Many Labels, Label-Efficient Panoptic Segmentation. We build our work on two main pillars. First, many recent visual panoptic segmentation methods rely on large datasets of densely labeled images. Creating such annotations is both expensive and laborious. Therefore, limited supervision techniques aim at relaxing this requirement by utilizing unsupervised or semi-supervised learning, as well as weak supervision, for example from point annotations. In this work, we continue to use dense labels, but decrease their number to as few as 10 samples. At the same time, we have seen the advent of foundation models in natural language processing, inspiring the vision community to propose similar methods. In particular, recent studies have shown that even unsupervised foundation models can yield image representations that capture detailed semantic information. Thus, we argue that foundation models offer a powerful pre-training strategy for addressing computer vision tasks in a label-efficient manner. In this work, we employ this paradigm to panoptic segmentation and propose a new approach for panoptic segmentation with few labels, which we call PASTEL. In our method, we leverage rich image features from a frozen Dino V2 backbone. Following a multitask design, we use two lightweight convolutional heads to predict a semantic map and object boundaries. Finally, we merge both predictions with a novel panoptic fusion module to obtain the overall panoptic segmentation output. During test time, we employ a multi-scale prediction scheme with overlapping image crops. Here we demonstrate our method for scale 2 with half overlapping windows. First, we extract an image crop. Second, we upsample this crop to the original image size and compute the features. These are then downsampled and placed in the location of the input crop. We repeat these steps multiple times. Once all crops are processed, we average the features of the overlapping regions. Finally, we compute the mean over multiple scales to obtain the overall predictions, both for semantic segmentation and object boundary prediction. These predictions are then fed to our panoptic fusion module. In step 1, we convert the soft boundary map to an infinity matrix, which we will use in step 8. In steps 2 and 3, we remove noise from the predicted boundary map and add boundaries between thing and stuff classes based on the semantic prediction. In step 4, we perform a class majority vote within enclosed areas, removing the burgundy red patch on the left vehicles. In step 5, we extract image blobs using the connected components analysis algorithm on the semantic classes. In step 6, we first process the thing blobs and employ multiple filters, for example to remove the red pedestrian patch from the rear window of the center car. In step 7, we employ similar filters to the stuff classes. In step 8, we use normalized cut to further segment instances of the same blob. Finally, in step 9, we fill holes caused by the previously employed filters using nearest neighbor-based label propagation. In our experiments, we observe that the quality of the predictions is higher for the images that are more similar to the examples in our training set. Therefore, we propose to bootstrap unlabeled images selected by feature-driven similarity sampling. Given the training set and an additional set of unlabeled images, we first create feature vectors for each image using the Dino V2 backbone. Next, we sample those images that have a high cosine similarity to the training set. We then use PASTEL to create pseudo-labels for the sampled images. Finally, we continue training PASTEL with both human annotated and pseudo-labeled images. We show results in the Pascal VOC dataset. First, we compare PASTEL with two previous label-efficient methods for semantic segmentation. PASTEL yields higher metrics, even when using fewer labels. Next, we increase the number of annotated images and the size of the backbone. Compared to the previous state-of-the-art ST++, we achieved an increase of 20.4 mean IOU. Note that we used less than 1% of the labels compared to the fully supervised method Panoptic FCN. We further provide results on the Cityscapes dataset. Compared to the recent Spino approach, our PASTEL significantly enhances the metrics by plus 3.6 mean IOU and plus 5.9 PQ when being trained with the same images. When increasing the number of labels and switching the backbone, PASTEL outperforms the previous state-of-the-art by 13.4 mean IOU. To conclude, in this video, we presented PASTEL for label-efficient panoptic segmentation. Please visit our project website for further information and the release code. Thank you for your attention.